Okay, so today I want to continue the study of the multiplication by n map, and just as a reminder of what we did last time. So last time we proved the theorem that says, I mean, um, so we proved the theorem. I mean, we take the multiplication by n map, and this is two. It has two coordinates. So gn hn, and we showed that gn over x evaluated at O is 1 over n squared, and hn divided by y evaluated at O is 1 over n cubed. Now, there is a corollary that requires a notion we talked about that is a leading coefficient. So note the function, the rational function x over y has a simple pole at O. That is a pole of multiplicity 1. And the reason is that the degree here is 2, and the degree here is 3. So when if you want like a heuristic reason, when we, instead of x, we can substitute infinity square, and instead of y, infinity cube. And then we get 1 over infinity. This is like a simple pole, this multiplicity 1. And if I have a rational function, then I can take x over y to the power of minus the order of r at O, and I multiply it by r. And this function, r has either a 0 or a pole, or the order of r at O is this orange number. And so when I multiply x over y to the power of this minus of this order, I cancel out. I have no zeros and no poles. So the claim is that this function is finite and non-zero at all. Okay, so this is a small trick, but if it is finite and non-zero, we might as well ask what is its value at O, and its value is called the leading coefficient. The leading coefficient of R is LC of R is exactly this function x over y to minus of the order of O at R times R, and all that evaluated at O. Okay? And as an example, we take R to be, let's say, 2x squared plus 7x divided by 2yx plus 2. So to calculate the leading coefficient of R, I need to calculate the order of R at O. So we can write, I mean, for U equals x over y, a uniformizer at O, we can write x over y to the minus 1 times R. This is 2yx squared plus 7yx divided by 3yx squared plus 2x. And so we get that the order of R at O is minus 1. Is yeah, I'm just checking if it is minus 1 or 1, but yeah, yx has degree 5 and x squared has degree 4. So O is a pole of R, hence the order is minus 1. And evaluating so now I want to evaluate yeah, actually maybe here there is an issue. So now I need to evaluate the x over y to the 1 times 2x squared plus 7x divided by 2yx plus 2. Um, but I have an issue. Mm. Okay, let me postpone this this example, and now we. I don't want to spend too much time on correcting it. My claim is that with this definition of leading coefficient, we can calculate the leading coefficient of Gn and Hn. And the leading coefficient, so I guess we can simply write it like this. One is that the leading coefficient of Gn is 1 over n squared, and two, that the leading coefficient of Hn is 1 over n cubed. Now, how do we prove this? The theorem shows that Gn has a pole, a double pole at O. And the reason is as follows. I mean, I take the uniformizer x over y at O, and I can write Gn as x over y to the minus 2 times x cubed divided by y squared times Gn over x. You see what I did here? I mean, I just added an, I mean, I added some x terms and some y terms to the numerator and denominator, and they all cancel out. But this is like u to the minus 2, and this is a function that is finite and non-zero at O. What is the value? Can anybody say what is the value of this function at O? I mean, remember, if you take the value, the theorem says that if you take Gn divided by x and you evaluate it O, you get 1 over n squared. So what do I get if I evaluate this product at the point at infinity?
The same.
Yeah, the same. And why? This here should be y squared.
Well, because the left side is going to equal to 1 because infinity over infinity.
Yeah, it's like, but the reason that x cubed, so I claim that this is, you can write it as x cubed divided by y squared evaluated at O times gn divided by x evaluated at O. The reason you can do it is because both of them are finite. This is n squared, sorry, 1 over n squared, and this is 1. You see why it is 1 there now?
Yes, because like each of them has like the degrees 2 and 3 respectively. So then like when you like the x is degree 2 and y is degree 3. So since you are powering them to 3 and 2, then all of like the thing is like power to 6 divided by power to 6.
Yeah, exactly. So this is 1 over n squared. But we don't care exactly about the value. All we need in order to calculate the multiplicity of a pole, we need a uniformizer to some degree times a function that is finite and non-zero at this point. So we conclude that the order of gn at O is minus 2. Now, okay, so now let's compute the leading coefficient. The leading coefficient is x over y to the 2 times gn evaluated at O. So how do I do this? I mean, this is like x squared divided by y squared times, but what I know to evaluate at O is gn over x. So I do gn over x here, and then here I do x cubed. Okay, evaluated at O, and this is what we just did. This is 1 over n squared. Okay, and exercise. Show the second part. Okay, so that's that is going to be quite useful when we study this gn and hn. But there is one caveat that I forgot to mention. So that is, if n is prime to the characteristic of the field. Okay, otherwise it's not true. This is also something that I should have said in when I restated the theorem. So this is also if n is prime to P. Now, now we talked about at the end of the last session, we started to talk about derivations. So I want to remind you what's going on. we want some kind of operator that will behave like deriving rational functions on E in a formal sense, because we don't really have analysis. This is supposed to be applicable to rational functions over finite fields, and then you don't really have like limit and the usual things that you have in analysis. But nevertheless, we want an operator which I will call derivation, and we wanted to satisfy the usual axioms that we are, or the usual properties that were used from derivatives of in ordinary analysis. So first we want that d of the constant rational function is going to be 0 for any element in the field. 2, we wanted the derivative or the derivation of a sum of rational functions is the sum of the derivations. 3 is that if I do derivation of constant times rational function, I get constant times the derivation of this rational function. And finally, we want that the derivation of a product is dr times s plus r times ds. And furthermore, we want, I mean, in K of E, the polynomial, let's say y squared minus x cubed minus ax minus b is equal to 0. And the derivation of 0 needs to be, 0 by axiom 1. So if I do derivation of this polynomial, I need to get 0. And this means, if you derive, you do 2y dy needs to be equal to 3x squared plus a dx. And so I set up axiom number 5 to be that dx is going to be 2y, and the dy is going to be 3x squared plus a. And then equation star is going to be true. And these axioms 5 and 6 can be a little counterintuitive, because the degree of x is 2 and the degree of y is 3. And usually in high school analysis, when you derive a polynomial, you decrease the degree. But here, because of our special setup, we in fact increase the degree when we do derivation. Okay? Now, I claim that there is only one one function D that satisfy all these 6 axioms. There is a unique D that satisfies 1 up to 6. So the proof is not hard. You kind of pull the string. I mean, for any integer, let's start by trying to derive x to the n. If you try to derive x to the n, you get, I mean, remember you have the axiom of a product, so you can try to derive x squared. If you derive x squared and you use axiom 4, then you get, I mean, well, let me just write what needs to be true, and then I explain a bit. So this is going to be d of xn, and you can see this by just checking a few simple examples. I mean, you do d of x squared. This is x dx plus x dx, which is 2x dx. So here it's okay. If you do d of x cubed, it's like d of x times x squared, which is d of x times x squared plus x times d of x squared. But d of x squared we already calculated. This is 2x dx. So I write here 2x dx. And I get 2x squared. So all in all, I get 3x squared dx. And you continue by a straightforward induction. You prove this. And similarly, if you want to do d of y to the n, this is going to be n y to the n minus 1 dy. And you see, this is this I didn't give it in the examples, but this also works for negative n's. So if we have this, we can then do the derivation of x to the n y to the k, because this is d of x to the n times y to the k plus x to the n times d of y to the k. Okay, and these terms we already calculated. So, but now I can use axiom 2 to extend this, to extend the derivation into any polynomial in E. So we can extend D to any polynomial over E. And now I want to do the derivation of a quotient. So instead of doing derivation of a quotient, let's start with a slightly easier case, the derivation of 1 over a polynomial. So if f is a polynomial, what is d of 1 over f? It has to be d of f times 1 over f squared. But now I can do the derivation of a product, and this has to be df times 1 over f squared plus f times d of 1 over f squared. And d of 1 over f squared, this is like, so I have df times 1 over f squared plus f times d, and instead of 1 over f squared, I write 1 over f times 1 over f. And now I can use the axiom that tells me what is derivation of a product. And so I get df times 1 over f squared plus f 1 over f times d of 1 over f plus 1 over f times d of 1 over f. So this is these f's cancel out, and I get df 1 over f squared plus a 2d 1 over f. So now I look at the start and I look at the end. I get like a recursive formula for d of 1 over f. So I solve the recursion. It's very easy. It's like I can just write d of 1 over f is equal to minus 1 over f squared times df. Okay, so this is just like you are used to if you in high school, if you do derivation of 1 over a polynomial. Is this clear? I don't want to rush too much. Nicolas, are you okay now?
I have.
No, go ahead, Alan.
So then you never get rid of the df or similar.
Yeah, I mean, eventually you can get rid of the d because you have axiom 5 and 6.
Right.
Yeah.
Okay.
But it's convenient to keep the d kind of implicit in some cases.
Okay, thanks.
This is like, it's like when I write here, I mean, if it was usual high school analysis, d of x is 1, right? So
yeah,
this would be neglected. I mean, cancelled. But here d of x, because of axiom 5 and 6, d of x is not 1. So I need to keep it in the loop. Okay, so but once I have d of 1 over f, I also have d of f over g. You take any rational function on E. It's like a quotient of polynomials. And I mean, d of f over g is d of f times 1 over g. And then I do the derivation of a product using this equation, but for g instead of f. And I get that the derivation of a quotient is d of f times g minus d of g times f divided by g squared. Okay, this is the usual formula for derivation of a quotient that you know from high school. And once I did this, I am done, because you see, I started by, like, I know, I mean, I know by axiom 5 and axiom 6, I know what must be d of x and d of y. And then from the rest of the axioms, I conclude what must be d of a polynomial. I mean, d of x to the n, d of y to the n, d of x to the n, y to the k. That you can push like a coefficient here, like a times x to the n, y to the k. That's not a problem. And then you can extend it to a polynomial, and eventually to a quotient of polynomials. And everything that we did here is this. I think that this is a situation in which the Arabic term of algebra is really suitable. I mean, algebra was called algebra by El-Khwarizmi, that said that this is the thing that must happen. And in Arabic, you say el-Jabr el-Mukabala, I think. And that's what's going on here. It's like, once you set up some natural axioms, there is only one thing that can happen. Okay, so is the proof clear? This is basically the end of the proof. There is we saw that you can extend d from d of x and d of y to the whole collection of rational functions, and you can do it uniquely because you have no choice in the process. You okay with the proof? All right. Then for any let's say let's do it in two parts. The first part is that for any r, the degree of d of r is larger by 1 than the degree of r. So d, in our case, d increases degree, contrary to the ordinary high school analysis differentiation. And two, if r is finite at p, so is d of r. Now, the proof of this is actually very easy. I mean, the first part is immediate, because we know it on x and on y, right? D of x is 2y. Yeah, 2y. Yeah, d of x is 2y, so this increases the degree by 1. D of y has degree 3, and x squared has degree 4. So d of y also increases the degree. And then you do products and sums, and so I should say, actually, is for any, instead of r, I should have written f, because degree is not really, we didn't talk about degree of rational functions, but rather on degrees of polynomials. Degree of d of f. Okay, so one is immediate. And for 2, we need to divide into 2 cases. One, if p is equal to O, or let's say if p is not equal to O, that's the easy case. If p is not equal to O, and R is some f over g reduced. So f and g do not have common divisors. Then if R is finite at P, then G or P is not a root of G. Right? Because if P was a root of G, then R would be non-finite at P. But then I do derivation of a quotient. I get, it doesn't even matter really what I get in the top, but I get G squared in the bottom. And if P is not a root of G, then it cannot be a root of G squared. And hence, P, well, d of f over g is finite at P. Okay, so this is for a P and not the point at infinity. For P, the point at infinity, if R is equal to f over g reduced, and finite at O, then there could be 2 cases. One is that the degree of f is strictly smaller than the degree of g. right? In this case, what would be R at O? R evaluated at the point at infinity. If I have a quotient of polynomials, one of them, I mean, the numerator is of degree smaller than the denominator, and I evaluated it at the point at infinity. What do I get? Exactly. Right, so this is 0, and indeed 0 is finite, and 2, if, I mean, it could be that the degree of f is simply equal to the degree of g. In case number 1, that's not a problem, because then I have d of f over g. This is d of f times g minus d of g times f divided by g squared. And I calculate the degrees. I mean, the degree of f, the degree of f, the degree of d of f is the degree of f plus 1. So here I have degree of f plus 1 plus degree of g. And here I have degree of g plus 1 plus degree of f. And here I have degree of g plus degree of g. So what I get is that the degree of the numerator, the degree of df times g minus dg times f, it's not necessarily smaller, but it's smaller or equal. It can at most be equal to the degree of g squared. And hence, when I evaluate d of f over g at O, I get something finite. Either 0 or some finite element in the field. And in the second case, is a bit more tricky. In the second case, it seems like we have a problem, because I look at the derivation of the quotient. I mean, the second case, degree f is equal to degree g. Let's say it's equal to n. Then the degree of the denominator would be 2n, and the degree of the numerator would be it could be 2n plus 1, right? Because the degree of f is n plus 1. Sorry, the degree of d of f is n plus 1. The degree of g is n. So the product has the sum of degrees. But if the degree of the numerator is bigger than the degree of the denominator, then when I evaluate it at O, it's not finite, it's infinite. So my only hope is that somehow in this difference, something cancels out. And indeed, suppose the leading monomials of f and g are, let's say, a times x to the k times y, let's say leading monomial of f, and leading monomial of g is it's something else, but it has to be of the same degree, and so it has to be also b times x to the k y. If you want, you can put y to the l here. That's also fine. And then when I do this df times g minus dg times f, I might as well, I can do it for each monomial separately. So when I do d of a times x to the k y to the l times b x to the k y to the l minus d of b x to the k y to the l times a x to the k y to the l, I get 0, right? Because the a here can get out, and then it's just a d of x to the k y to the l times ab times x to the k y to the l. So the leading monomials in the numerator here cancel out, and that's why the degree of the numerator is at most, I mean, maybe more monomials cancel out, but the degree of the numerator is at most 2n. The degree of df times g minus dg times f is less or equal to n, and therefore d of f over g is finite at all. Okay, so this finishes the proof. Questions about the proof? Is it clear? I mean, I tried to cut it down to small pieces, but maybe I can repeat if Nicolas, now? Okay. So let's take a break, and leave it in 10 minutes. Okay, can we start again? So the next thing we want to do is a rather central proposition. We want to be able to relate the order of a rational function to the order of the derivation of this rational function. And the claim here is so let R be a rational function if the order of R at P, which we will denote as D, is non-zero and prime to the characteristic, then the order of the derivation of R at P is D minus 1. And the proof here, suppose a U is a uniformizer at P. And then I can write R equals U to the D times R times R1, where R1 is finite and non-zero at P. Then I want to derive R, but if I can express R as a product, I can simply derive the product. So D of R is D times U to the D minus 1 times du times R1 plus U to the D times D of R1. And now I can take a common factor U to the D minus 1. And I get D times du times R1 plus U times dr1. Now, when I evaluate this term at P, this guy is 0 at P. Because U is a uniformizer at P, it means that U of P is 0. So whatever D of R1 is, I mean, well, I need to know that D of R1 is not infinity. But how do I know that D of R1 is not infinity? So let's try to evaluate U times dr1 at P. I want to write U at P times D of R1 at P, but I can only do this if both of the factors of the product are not infinity. I mean, if both of them are infinity, that's okay. Then they could be infinity. But if one of them is zero and one is infinity, I cannot do this. So I need now U of P is zero. So I need to know that D of R1 is not infinity. How do I know it? I mean, R1 at P is not infinity, right? If it's not infinity, it's finite. We had a proposition, you remember, before the break. Anybody? Nicholas, what do you think?
Yeah, I don't know.
I mean, remember the proposition. We had a proposition that said that if R is finite at P, then also D of R is finite at P. Remember, it's here. If R is finite at P, then so is D of R. You see, now I apply this proposition not to R, but to R1. R1 is assumed to be finite at P. So D of R1, by this proposition before the break, D of R1 must be finite at P. Is finite by a previous proposition. Okay, so whatever it is, I don't care because the other factor is zero. So this is zero. So in order to prove that D of R, I mean, we want to show, remember, that we want to calculate the order of D of R. And we have a guess. I mean, this is what the proposition says, but it's also quite intuitive that the order of D of R should be less by 1 than the order of R. So how do I calculate the order of D of R? I mean, at P, I need to write it as U to the D minus 1. If I want to show that the order is D minus 1, I need to write D of R as U to the D minus 1 times something that is finite and non-zero at P. Now, what I have in the brackets is a sum of two things. One of them, this is in the orange, is zero at P. So if I want to show that the sum is finite and non-zero at P, what I need to do is to show that D of U is a finite and non-zero at P. If it is the case, then since R1 is finite and non-zero at P, then I will get D times something that is finite and non-zero at P times something that is finite and non-zero at P. So this is plus 0. So all in all, I will get something finite and non-zero at P. Is this clear? I have a feeling I lost you here. Anna, what do you think?
Yeah, a bit lost. You're right. I'm rereading the like the proof to try to.
Okay, so let's just. I mean, we didn't do a lot of the proof, so I mean, we can just go over it. I mean, we want to show that you take a rational function and you take a point. Of course, I didn't say it, but a point on the curve, and just like we, I mean, there is the, I mean, the order of the rational function r at the point p. This is some integer. If p is not a zero or a pole, then this integer is zero. But let's suppose that p is either a zero or a pole. So this integer is non-zero. Either it's positive or negative, and we assume that this integer d is prime to the characteristic. Then I claim, I mean, or the proposition claims that, I mean, d of r. Remember, d is like it eats a rational function, and it spits out another rational function. I mean, you plug in r and you get d of r. So d of r is a rational function. I can ask what is the order of this rational function at p. So is the statement okay?
Yep. Thanks.
Now, okay. So now we start the proof. We have an assumption. The assumption is that the order of r at p is d. What does it mean? It means that for a uniformizer at p, I can write r as u to the d times some other rational function, r1, such that r1 does not is finite and non-zero at p. This is by definition what is order of a rational function. And then, okay, but if I can write this, and of course, u here, u at p, because this is always true for a uniformizer, uniformizer at p is always zero. And now, because I can write r as a product, I can do d of r is like d of a product, right? Do you now do you understand this line? How I did the derivation?
Yes.
Okay. And now this line, I just take a common factor. I take u to the d minus 1 as a common factor. And I want to show that the order of d of r at p is d minus 1. In order to show this, I need that I would be able to express this rational function dr as u to the d minus 1 times some other rational function that is finite and non-zero at p. So far, it's okay? And in order, so this other rational function, you can call it R2. R2 is a sum of two things. So in order to show that R2 is, okay, is finite and non-zero at p, I can just evaluate each of the summands at p. So first I evaluate the second summand. The second summand, I claim that it is zero at p. This is the orange thing. Why is it zero at p? U at p is zero, right? This is like the basic property of a uniformizer. Uniformizer at P is always 0 at P. And then the second factor, D of R1, evaluated at P, it has to be finite, because we had a proposition that says that if R is finite at P, then also D of R is finite at P. And so we apply this proposition to D of R1 instead of D of R. And I get that U times D of R1 at P must be 0, because it is 0 times some finite, some finite value. Is this clear now or no?
Yes, thank you very much. Thanks.
Okay, and now, so in order to show that R2 at P is different, is finite and non-zero, I might as well, it's enough to show that du at P is finite and non-zero. Because if it is the case, I know that R1 is finite and non-zero at P, and it will be a product of finite and non-zero rational functions. Okay? Now, Nicholas, you with me?
Yes.
Okay. So how do we show that du is finite and non-zero at P? We do the usual cases. One, if P is let's say A comma B, not the point at infinity, and not of order 2. Then what is the uniformizer? The uniformizer for P, such P, is x minus A. So what is D of U? D of U is simply a 2y, right? This A is a constant. I don't care about it. And indeed, if I do du evaluated at P, this is like 2y evaluated at P. This is B, sorry, 2B. And 2B is different, is not 0, because P is not of order 2. The only points that have a second coordinate equal to 0 are points of order 2. So in this case, we are fine. Is this clear? And now, second case, what is it? If a P is, let's say, some omega comma 0, of order 2, then the uniformizer for points of order 2 is simply y. So D of U is 3x squared plus A. And 3x squared plus A, it's, I remind you, this is the derivative of the x polynomial of the elliptic curve. Now, omega is a root of S of x, and not a double root since E is smooth. And hence omega cannot be a root of the derivative of S prime x, which means that du at P is some finite value that is non-zero. Is this part clear? And now, what do you think?
Yes, the thing that I don't remember, like so E is smooth, and this means so this means that can.
So what? Yeah. So if you remember, when we talked about the in the very start of elliptic curves, the definition of elliptic curve has a condition that the discriminant is non-zero.
Okay.
Discriminant of the elliptic curve being non-zero, the discriminant is something that is related to this Sx. You remember? Sx is simply Sx is like the x cube plus ax plus b. Okay, and the discriminant, I forgot the formula actually, but the discriminant being non-zero means that this polynomial S of x has no double roots. I mean, it has over the algebraic closure, it has three distinct roots.
Okay.
So I'm claiming, and this is what we call smoothness. This is because it was equivalent to the condition that we have a well-defined tangent line at every point. Okay.
I see. Thanks.
And now okay. So if P is of order 2, then it is of the form of omega comma 0, where omega is a root of S of x, right? It's like it's like these points. Like you may have, it's like the points that intersect the x-axis. So it's all roots of the polynomial Sx, and they cannot be double roots. But if something is a root of a polynomial and not a double root, it means that it is not a root of the derivative of the polynomial. You see? So when I substitute omega here, I can be sure that 3 omega squared plus a is non-zero.
Nice.
And substituting omega is just substituting a p in d of u, right? So I conclude again that du at p is non-zero. Nicholas, are you okay with this?
I think so.
Okay, and then final case.
In the chat.
Lisa, yeah. Lisa, is this okay now, or because you wrote it a while ago? Okay, so the final case is a P is equal to O. If P is equal to O, then the uniformizer is x over y. And then what is d of u? D of u is, I have a formula for derivation of a quotient. And if you do it, you get x cubed divided, well, not x cubed. You get 2, I mean, you get the derivative. Let's do it. You get the derivative of x times y minus the derivative of y times x divided by y squared. But the derivative of x is 2y, so I get 2y squared minus the derivative of y is 3x squared plus a, but times x, this is times a times x, and here I do 3 cubed, and here I put minus. Divided by y squared. And okay, and now I need to get rid of this. Wait, it's not a problem. Yeah, so evaluated at all. I don't want to do the calculation, but we don't care. This is finite. This is finite and non-zero. Because the degrees are equal. Right? The degree of the numerator is, I mean, either, y squared has degree 6, and x cubed is also degree 6. So here the degree is 6, and here the degree is also 6. So when you evaluate it all, you get some finite non-zero number. Okay? So this concludes the proof. Let me give you an exercise. From the proposition of show that if a rational function u satisfies u of p is equal to 0, but du at p is not 0, then u is a uniformizer at p. Okay, this will bring you back to the definition. You will need to refresh the definition of uniformizers, and also go back a little bit about the properties of the derivation. So I think it's like a nice it's a nice thing to do. the next thing that we want to do is to calculate the derivation of Gn. This is going to be 2n Hn, and the derivation of Hn is going to be n times 3 Gn square plus a. Yes. Who ask a question? What is the Fn? What do you mean by the Fn? No, the d. This is the function d. It's I mean, we basically showed, because if you think of it, I mean, it's like you can think of it as like pulling a string. I mean, we know how to do d of x. But I mean, we are forced by the axioms 5 and 6. We are forced to get the value of d of x and d of y, and then if we want axioms 1 up to 4 to be satisfied, then we have only one way to do d of x to the n and d of y to the n, and then also d of x to the n, y to the k, and then d of any polynomial. And then by this property, we get a d of any quotient of polynomial. And any rational function is a quotient of polynomials. So we basically, we had no choice. It's like we I mean, if you had another, I mean, why is it unique? If you assume by towards contradiction that there was another function d prime that satisfies axioms 1 up to 6, then d and d prime would agree on x, and they would agree on y, right? D of x would need to be d of x, d prime of x, and d of y would need to be d prime of y. And then d of xn would have to be d prime of xn. Okay? And so on. So all the things we did is like we had no choice. It's this الجبر المقابلة. Okay, so what's coming up is this calculation, and this will be next time, I guess, because it doesn't make sense to start it now. But what we will do, I mean, using the derivation of Gn and Hn, we will be able to pin down the zeros of these functions. The zeros of this function are the so-called n-torsion points. So this derivation will come very handy in understanding torsion points of elliptic curves. All right, let's request before we take. I mean, we will meet again only on only on the 9th of August. So I will check the Discord channel if you. Yeah, I'm sorry, but I mean this. I go to a conference, but it's also maybe good to do a summer vacation. We are not far from starting the whale pairing. I imagine that we need something like 2 or 3 sessions to finish the end torsion points, and then we're more or less ready. Okay, so
Nice.
yeah, I think it's going in good pace. All right, so have a good weekend and a good time off.
Thanks.
Bye bye. Have a nice trip. Bye.